So what we're going to cover is how to represent the network, pipe properties, and we started to use pipe properties a little bit, but it's important to think about some of those elements in pipe property. Water use and demand, and what do we mean by demand, how to apply the model in different ways, and then how to look at the results. That's my favorite one, is looking at the results, because there's so many ways that you can slice that and graphically represent things with color coding. So many different ways you could do that. So I like that one, that part of it. Here's the spoiler alert. Your model is only as good as the software plus the data. So even if you had the Rolls-Royce of software and you had horrible data, or data that was not verified, or elevation data that was eyeballed off of a USGS map background or something, it doesn't matter how good the software is, the data is still a little bit shaky. So your model is going to be a little bit shaky. Software can't make bad data good. It can kind of help and show you where bad data may exist, but don't expect more of the software than the data that you can give it. And keep in mind, model is an approximation of the real world. And I'll say that as many times as I possibly can, that it's an approximation. So if you're looking at decimal place precision, you probably need to be backing off on the decimals a little bit, because I'll begin to show you why when we get into calibration. Keep in mind, it's just an estimation of the real world, because there's so many unknowns out there under the ground. And again, the approximation is no more accurate than the data you give it. So all in all, that means garbage in is garbage out. And you're going to spend a lot of your time checking results and checking input data. That's, it's fun to do the modeling, but the hard work comes in is verifying data, verifying the piping network, verifying C factors, verifying pump curves, making sure all of that's right, because it's so easy to put the data in, but you got to verify that it's correct data. All right. So the workflow that you might follow along in the modeling process for a particular model is to first define the scope of the model. And the software is really capable of doing a lot of things, but once you define the scope, that's going to let you know what type of input data you're going to need, what tools in the software you're going to use, and are you prepared or are you trained on how to use that tool. And it also kind of lets you know what's the extent of calibration data you need to collect. So define the scope, and then that helps speed some of the downstream steps of what tool you're going to use in the software, what data you need to enter. And now, once you have those questions answered, then you start entering data and verifying it. Learn how to use the software for the tool you're about to use. Enter the data, build your model. You have an initial model, right? So in this first workshop, you drew your initial model. The very next thing you would do is calibrate your model. Rather than just go leap to design decisions, you would calibrate your model. And we've got a whole topic in a couple-hour session. Let's see, tomorrow on that as well. Well, on Wednesday, I'm sorry, on calibration. And we're going to spend a lot of time, because it's so important to have a calibrated model rather than just kind of jump in and start making decisions that are worth millions of dollars. Once you have that reliance on a calibrated model, you can start setting up alternatives and scenarios. In the next few slides, in a little bit, we're going to talk about that. So we'll get to that. And come up with your scenarios, look at your solutions, do color coding, and then come up with results for your model, whatever the set of pipes are, whatever the pump size is going to be. Those are your results. So to define the scope, that first step, the modeler is going to need to go ask around. Probably, if this was a municipal organization, a public entity, they'd probably have several departments that the modeler would want to get information from. The engineering department would give standards for, say, pipe diameters, minimum pipe diameters, things like that, the plans, the what's currently being worked on. The planning department would actually give, here's the future stuff that's coming. Here's the future connections that are going to be there that you as a modeler would want to know about. And then the operations group is going to be, if there is a separate group like that, they're probably going to have a lot of the controls and operations for the network. that are really important, as you're going to find, to set the initial conditions and trigger when things go off and on. Important group to interact with, and also to see what their needs are of the model as well. So maybe the engineering department is trying to do increasing diameters of pipes in a certain area, and they're going to have some requirements. Maybe the operations guys, they want to change the configuration of the network to save energy on the pumps. So that's a potential requirement of you as a modeler. And then what information might you get from senior management? Budget. How much time are you going to be able to spend on the model? What are the goals of it? How thorough can you be, basically, is what that might answer for you. Okay, so identify those parties, and quite often there may be 5 or 6 other groups that you may have to interact with. It might be a bit more complicated sometimes. Select the software, and here's the first spoiler alert again. Most software packages work. They all use Hayes and Williams. They're probably going to come up with some of the same decimal place accuracy. Whether it's Hayes and Williams or Darcy Weisbach or whatever hydraulic formula it's using, it's probably going to come up with the same values. However, how you got there, the journey you got there, how easy it was, and then how you represent and easily use or recycle that information for future designs, that's where the differences in software start coming in. Extending that further, what does the support look like? How easy are the tools to pick up and learn? What are the qualities of the manuals? Do they have classes? What's the interoperability of the software? Can you actually operate and manipulate a geodatabase, or do you have to go through 3 or 4 steps to do that? So there's differences, obviously, in the software. All right, next thing you do, you learn how to use the software. And also, as you've been seeing, there's posts to the hydraulics and hydrology community, big communities out there. It's a great source to go to get kind of on the cutting edge of how to use the software and improve your techniques. Okay. Now we're going to start getting into how you build your network and where did you get the information from to build the model. You could be converting the maps, converting the model from actual paper maps. Maybe there's some automated or semi-automated, or hopefully not too much manual process to bring it from CAD to GIS into your model or something. Maybe there's a large geodatabase and you just simply need to connect to that geodatabase to bring that information in. And within the hydraulic model, you're actually going to then start drawing elements, and you'll have different various elements to use, a pump, a tank, a reservoir, things that you've already seen before. You're going to pick these elements and draw them, and you could have some really complex ones, a surge tank, rupture disc, turbines. These are all elements that you can draw in WaterCAD and WaterGEMS. However, to actually run some of these elements as if it were a transient analysis, that would actually be using the product Hammer. But it's the sister to WaterCAD and WaterGEMS to give you transient analysis for your system. Okay, so there's the elements. Now let's start talking and getting into the diameters. It's really important for the diameters in your model to know that they're accurate and correct. So let's go through the thought process a little bit here. Would you use nominal diameter or actual inside diameter? Nominal would be, say, 6-inch, 8-inch, 10-inch. Or convert it to metric. It's whatever you would buy off the shelf. You would order a 6-inch pipe. You would order a 10-inch pipe. In a hydraulic model, which would you use? And when we're thinking of, let's see, the Hayes and Williams equation, inside diameter would be the pure answer. That would be the pure value, because it's actually what's carrying the flow, and it's what's driving the Hayes and Williams equation. And for example here, I've given you the difference, a few differences in class of pipe. And if you order a 6-inch GI50, that's going to have 6.4 inside diameter. If you order a 6-inch GI56, 6.04. That one's really close to 6-inch, but the other one's got more capacity. Now, generally how this works is the inside diameters are going to be more than the nominal. So again, actual diameters are generally going to be more than the nominal. So 48-inch, again, it's 49 something or 48 something. It's not 47 something. So there's a little bit of a cushion there for you to consider. That now, let's say you have a model and there's 1,000 pipes in there. And not every one of those pipes are created equal. Some are different pipe materials, some are different classes of pipes, and they range. So yes, you can go to this level of detail and verify by family, by installation date, or by class of pipe and diameter what the actual inside diameters are. That would be the purest way to do it. However, that's going to take some time. So if you didn't have the budget to go in and do that and spend all the time to do the research, it may not be something that you're going to be able to fit in. And remember, on the bright side, nominal is going to be smaller than the actual inside diameter. So there's a little bit of cushion. So it's okay to be a little bit smaller and err on the safe side by running with a nominal. It's okay. It's not the end of the world. But if you're trying to go highly precise on your model as much as you can, do the research, but it's going to take some time to verify all of the class of pipes. And then also, you can consider 3D length versus the actual plan length of pipe. So all this is going to Tools, Options, Project, use 3D length. And to be honest, it's not going to make that much of a difference. If you want, you can turn this on and it will consider the 3D length. If you boogered up any of the elevations, it's really going to show, meaning it's really going to make a big difference. Whereas if you don't have, if you that boogered up elevation somewhere, just in plan view length of pipe, it's not going to be that big of a deal. So if you choose to use 3D length, just double check and make sure that your elevations on your nodes are right, so you don't have some super long pipe going down to 0 elevation. Okay, elevation, another one since we're starting to talk about nodes. Which reference point would you use for your nodes? If you're going out into the real world, you're out in the field, you're standing there, the pipe is below grade, generally. Generally it's below grade unless it's some overhead pipe or something. Generally it's below grade. If you're going to test the pressure on that pipe, where do you test the pressure? Under most circumstances, we're never actually down at the pipe level. We're a couple feet above. And that couple feet above is actually a pressure change because we're going higher, right? But generally, you're testing pressure at a hydrant. So that's the relative elevation point that you would be comparing to. What's easier, to get the elevation of the ground or the elevation of the pipes for 1,000 pipes? Which one of those would be easier? Okay, ground. Ground wins. Right? It's easy to get ground. To get pipe elevation centerline, you'd have to go to construction drawings, and even those not be right. You might have to go to as-built, and it's going to get more and more difficult and time-consuming. So ground elevation wins for a couple reasons. A, because it's easier to get to, and then B, because it's going to be closer to your sampling point. So let's think through this now a little bit again. We already kind of talked about we're not going to use the pipe because we're not digging a hole down to the pipe. We're actually sampling, in this case, where the hydrant is. Maybe your handoff point is a meter. And that's another reason why ground would win too, is because the handoff point from a municipal organization to a private owner, property owner, is generally at the water meter. And that water meter is generally, okay, half a foot below grade or something, a third of a meter below grade, but it's pretty close to ground. And that's generally where a node or a junction somewhere, or a water meter in a basement, okay, okay. Maybe there might need to be some unique adjustments for the way your system is laid out. But generally it's wherever that handoff point is. Where you might want to use something other than ground elevation is when you're comparing a sample data point. So this is ground elevation. but our sample point is here. And this could be a foot, 2 foot, 3, 2.5 something. I don't remember the exact measurement off the top of my head, but there's a height difference there. Definitely from the ground up to the sampling point. So if you're going to compare the model, your hydraulic model, to the real world, it's best to compare that using the exact elevation, or close to it, as close as you can get, of the sampling point connection. That's where you're going to strap on the pressure gauge, right here to the hydrant. Not here by the meter, not here in the ground. You're connecting the pressure gauge right here at the outlet of the hydrant. That's the elevation, ground elevation you would use for that node because it's a sample data point. And now you can really start comparing pressure gauge data in the real world to pressure gauge data in the model. So it's pretty important to pick up on this one too, that wherever you're comparing data points to, make sure that those elevations are the correct ones. Sometimes the pressure gauge may be on a riser pipe somewhere. This is a picture of a digital elevation model. Right here on top, it's a nice, pretty looking elevation model. And there's a network underneath. And our tool inside of WaterCAD and WaterGEMS is called T-Rex, or Terrain Extractor. And what it effectively will do for you, automatically, is wherever the node exists in reference to that digital elevation model, it will pick out the elevation data point. So for this node, it maps to this X and Y coordinate, and it picks off that elevation. And it does that in a blink of an eye, provided all of your data, all of your nodes are within that digital elevation model. And it pulls that automatically for you and loads the elevation on all of your nodes. Okay, so where do you get this information from? You get it from topo maps, the elevation data anyway, survey maps, DEMs, maybe you've got the files in GIS somewhere, and you just export them as a shapefile. Maybe that's what you do. Next part is you have the network in, you have the diameters, you have the elevations. Now, how do you put in how the model is going to draw water from the system? Meaning, how are the nodes going to draw water away, and how much volume, and how is that going to work? Are you going to model it as individual meters in the system? Are you going to model it as, well, it's a commercial area here, and there's so many gallons per day per acre. This one's residential. That's got gallons per day per acre. Maybe it's very coarse data, or maybe you like the more precise data where you've got all of the meter elements for the entire system. Somehow you need to represent the demand on the water network. When you do this, you need to consider all of the use of the water, meaning how much flow do they use, but then also unaccounted for water. Maybe there's different, a lot of times you'll see this, municipalities don't meter themselves sometimes, so you have flow going to irrigation, pretty significant amounts going somewhere that aren't metered. Hydrant flushing, maybe that's not properly recorded. It should be, but it's not properly recorded sometimes for hydrant flushing. Meters that aren't functioning properly, maybe it's such a low flow on the residential side, there's a leak that the meter's not even moving. That's a possible one. And then there's another good one, fire. A lot of times it's supposed to be documented, but how that's done is just perhaps measuring the time that the fire started and that the fire was put out. And it's very rough. We had a certain number of trucks, and each pumper truck has a capacity of a certain amount on the pump, and it's very rough estimates, not really relative to how much pressure was in the supply system itself. So lots of different places that you can get unaccounted for water. So now your challenge as a modeler is the demands that you're modeling, are they taking into account all of this appropriately? And if you're comparing your model data to pressure gauge data, was that pressure gauge data taken when there was a fire event, when there was a flushing event, with any of these variables going on? If so, you need to include that in your demands. Now, let's think about placing demands in a real model for your system. There's these nice, pretty little houses, and we have J35 and J36. So now you as a modeler, you know these houses are out there. Where would you put the demands from each house? And let's say, for example, each house, just for argument's sake, is 1 gallon a minute per connection. We'll just make easy math here. 1 gallon a minute per connection. 1, 1, 1. how would you load J35 or J36 with these houses? Different schools of thought. Some might just say, okay, well, these, I'm going to grab them because they're closer. These go to here, and these go to here. Okay, fine. For this area of the system, you make a decision to do that. Well, when you zoom out a little bit, it really starts to matter a little bit less. And when you zoom out some more, it matters even less what you did at this one junction or these two junctions and how you split it up. However, using the load builder tool to automatically load the network, it allows you to do things however you need to. There's a lot of different options in there. But we also have customer meter elements that actually are like little houses. It's a little black house symbol with a chimney and everything, and you can actually place that wherever a meter is, and then have that connect to the nearest pipe or nearest node, meaning it would be referencing the nearest pipe or nearest node. So that way, exactly where the meters are, you have a symbol for the meters, which is a house or it looks like a factory or something, however you want to interpret it. And that's the demand that's going to be pulled off of the system at that point. And then you can specify whatever lateral size you want to use at that point. So that's a new element that came on a few versions ago. As you load the model, are you going to load it for current year, current average data? What type of peaking factors are you going to apply to get it to be able to model the maximum day? Are you going to consider fire flows? How many fire flows? Are you going to consider unaccounted for water? And what percentage is that going to be? Are you going to uniformly increase all of the demands by a certain percentage for unaccounted for water? These are questions that, again, you get paid to do the big bucks. The software's not just going to do it for you. You actually start putting the thought process behind it to make sure your numbers are accurate. And then what is the future going to look like for your model? So here's a quick way to think of it. If you had a system production and you had all the system production is coming from a water treatment plant, that's your source. It's feeding the network here. It's one treatment plant. We're going to make it real simple. Some of the flow then goes to sub-areas. Maybe it's going to sub-zones. And then maybe some of the large water users, you already know what their water meter data is. You've got that. That's no problem. Great. But then some of the data goes on out into the rest of the system to the nodes, and you're not quite sure how accurate that is because it's, there's flow meters, but there may be water loss and unmetered flow and flushing and all these other things. But the nice thing is whenever you are loading the network with all of the flow that came from the treatment plant or the meter that came from the supply that the city purchased the water from, you know how much water went through there, and wherever that's going, it's going to be feeding the water loss, the fire flow, undocumented fire flows, the undocumented irrigation by the city, the water meters that are poorly reporting data. It's taking into account all of that. You just now have to spread it out appropriately to all of the nodes. Now, thinking about it from the other direction, from the bottom-up method, you know all of the customer meter data. And you can load all of the customer meter data to all of the nodes. Okay, that will work. However, you know how much water was only metered, not how much water was lost. So you would still need to accommodate that deviation. Just kind of throwing some numbers out here. Unaccounted for water could sometimes be on a municipality that's running pretty well, maybe 6-7% unaccounted for water. I'll go ahead and say the largest one I ever saw was about 50% water loss. And at that point, you're pretty much opening the door and just shoveling money out the door. I mean, 50% loss is a pretty substantial amount. But it's a measurable amount that is not metered that is lost. So however accurate you want the model to be, taking into account unaccounted for water is important. This may begin to look more like a mass balance. In situations where systems are so big and the water loss is so high, there's an approach of dialing down the pressure at night to minimize water loss. Because the less pressure behind the orifice, wherever those leaks are, the less water that's lost. And then during the day when people need the water or to put out a fire or something, pressures increase. Yes, you lose more water at that point, but at least it's not happening during night. Loading your model by flow meter data is the most accurate method of loading the data and putting demand data on your network. One of the least accurate methods would be based on the acreage of a certain area and the nodes that are within that acreage or that lot or that district or that area. You can load it by how many gallons per day per acre, because geometrically you would know how many acres that area represents, and then you could say 2,000 gallons per day or whatever demand rate you would say. That's going to be kind of one of the least accurate because you're assuming whatever that rate is per acre per area, as compared to flow meter data that is a lot more precise. When you would use a method like this to load a model, that would be planning or some future kind of model, and you're not quite sure what's going to go there. So probably not a very common one if you actually have flow meters in the area. Peaking factors and figuring out what demands are going to be in the future. What's it going to be like in 2030? Where your demand's going to be, average per person. Different countries, the demand per day per capita is different based on living conditions, based on whatever the needs are. But when you're looking at a future hydraulic model for, say, 2040, do you project that the demands per capita per person are going to be increasing steadily, will be linear, some innovative technology will come online and reduce it, or are you implementing drought water restriction plans for a city henceforth? So you anticipate gallons per day per capita will be decreasing, although population may be increasing. Looking at a model for 2040 or something like that, you need to start taking into account what's the demand going to be. Now, you generally need to you might want to be asking someone else to sign off for this, because it's pretty much committing to what something's going to be in the future when it's reading from the magic 8 ball. You want somebody to be responsible for that decision, definitely. Maybe, and again, an example of some high, innovative technology that might come online and, wash your clothes and then use your toilet or something. Just dreaming there. Okay, so you've got your network, you've drawn your pipes, you've loaded it, and now you're about to start modeling. So maybe you're going to skeletonize your model. And what this is an opportunity for you to clean up things in your model that may not necessarily need to be there. How skeletonization works is it takes the full database, runs it through a skeletonizing program, and you end up with a subdata. It's unidirectional, so I'm going to caution you, if ever you want to entertain the idea of skeletonizing, keep in mind it goes one direction. It doesn't go both ways. If you want to go back the other way, it's going to cost you money. It's going to cost you time. Here's an example of a skeletonized model on the left, full all-pipe model, and skeletonized model on the right. The one on the right, less pipes. However, hydraulically, it's still behaving the same way because we have equivalent pipes. And I'll show you more of how that works later on, but for now, let's just suffice it to say, hydraulically, they behave the same. A pump would never know the difference, but there's less pipes. Another example of skeletonizing, if you skeletonize the model and had data measurement points at point A and point C, hydraulically, running a skeletonizing program or the skeletonizing routine, A and C would still come out the same. They would still be measuring the same pressures because you have equivalent pipes with equivalent diameters. However, if you were looking at comparing pressure gauge data at B, oops, there's no B in the skeletonized model. So this would be an example of why you wouldn't want to skeletonize, is because you might actually take away one of your data points. The reason you would want to skeletonize might be to do some master planning. It might be to do regional water quality studies or energy studies. The reason you would not want to skeletonize a model is if you're designing some flushing routine using the flushing tool in WaterGEMS or WaterCAD, looking at water quality studies, chlorine decay, you're doing fire flow analyses, the model can not predict as well as the hydraulically as well as it should if you're starting to limit the numbers of connections or reducing the loops, which is what skeletonizing begins to do at some point. Then once you've got the model skeletonized, if you needed to, maybe it's just laterals. Maybe I'll take a step back. Maybe you just want to take off the laterals in the system or remove pipes in series and simplify the network. That's an example of skeletonizing. That's not bad. It's okay. It just helps you move faster as a modeler. Once you have that done, it's time to calibrate your model. And this is where you're collecting field data, verifying that your hydraulic model matches that field data. And where it does deviate, you alter the hydraulic model to make sure that it's going to converge on the real-world data as best as possible. And once you have that set up, now it's time to start doing the modeling. If you're doing pump sizing, you would put in pump curves. If you're doing energy costing, you put in the cost of energy and any rates. If you're doing water quality analysis, you'd put in the decay rates for chlorine. And let's see, if you're doing flushing, you put in the size of the hydrants. Valving criticality, you would actually be putting in the isolation valves and whatever you consider to be an isolation valve. So you would add a little bit more data and a little bit more information so that the model can run based on whatever it is you're trying to do. Okay, now speaking about runs, how a hydraulic model works basically is there's an input file, you run the model, and you get an output file. Kind of in the old days, there was one input file for every output file. Well, we're not quite there anymore, and we have something now, an innovative tool here to use called a scenario. And this question had come up often earlier is, what is a scenario? And a scenario is a what if. It's a type of run. It's a single run. You can keep running it, go back and run it, change something, run it, change something. But it points to a set of alternatives. And these alternatives are what I was referring to earlier as building blocks. These building blocks are a data set for all of your pipes and elevations and diameters, and it's a physical data. It could be your initial conditions data, and I'll give you some more examples of what alternatives are. But they're basically the pieces that you add together to come up with a what if. And then you're going to learn how to leverage inheritance. And inheritance is what you use inside of your alternatives to save you a lot of time, to keep you from having to update lots of other different pieces of data. You can just update it once and it matriculates all the way through. So how a scenario, again, I'm going to spend a little bit more time on scenarios before we get back into the inheritance of alternatives and what that exactly meant and what I was even talking about. So I'll give you a little more detail in just a moment. The scenarios, you'll build a scenario like you did in today's workshop, calculate it, review the results, and add a scenario. That was the pattern that you were in today, and you created one with new diameters. And today, you only used really the physical alternative. You created a physical alternative, and I think maybe you added a demand. You did add a demand there. So you added two building blocks together to make a scenario. And your initial settings did not change. The tank water elevation stayed the same. But let's say you wanted to run a model with high water surface elevation in the tank and low water surface elevation in the tank. Run two different scenarios and see which one's worse. Chances are pressures would be lower when with the scenario with the tank water level lower, right? You kind of know that, but this is how you would prove it. You would have two alternatives for initial settings. One tank with tanks at high water level, one with tanks at low water level, and have two relative scenarios to run that with. To use one scenario to use each of those building blocks for initial settings. Maybe for water quality, you wanted to run a scenario with a chlorine decay rate of one value, and then run it again with a chlorine decay rate of another value. So you would use an alternative, constituent alternative there. And maybe you're looking at changing the pump operation to see which one's going to use the least amount of energy. You would set up different alternatives for operational alternatives and have scenarios that would use each of those. So scenarios are what if, alternatives help you build that what if and make it happen. So very quickly, here is how scenarios would work. This is one physical alternative that you see on the screen. The green that got added with active topology, we turned some pipes on. Active topology is another alternative. Our demand's increased, so there's another demand alternative. Demand alternative here, and active topology went on. Here's another active topology. We turned another set of pipes on. So now we have another active topology alternative, and we're at a different year, so we've got different demands. So we're using different building blocks to come up with another scenario. And maybe we want to turn this pipeline on and make it a larger trunk line. So that's an active topology. We've turned another pipeline on. Maybe we change the diameter to. It's in physical. So these building blocks can help you kind of methodically go through and test the changes that you're going to do on a model. Now the important part that you need to walk away with WaterCAD and WaterGEMS and how it helps you handle all these things is you have an initial base model. And on day one you have a base model and you create a what if I'm going to increase the diameter here at this pipeline. Then with a child alternative, again, I'm sorry, I forgot to mention this is a child right here. You made a child alternative, child here, child. And this subset right here shows you, I'm just indenting, so that's a child alternative. Then you make another child alternative, and instead of having to update this pipe diameter here, you don't have to do that anymore because it's referring to the parent, in this case physical alternative 1. And you're only making a change to this pipe diameter. And then as you go one level deeper into the child inheritance, you want to change this pipe diameter, but since you made it a reference to physical alternative 2, which referenced alternative 1, which referenced base, you only had to change one pipe diameter. So really and truly, you only had to change 3 pipes in here. Now let's add on something like Mr. Modeler, Mr. Modeler, Miss Modeler, the base model, all of the pipes in this area, 50 pipes, they're all the wrong diameter. We put in the wrong information, so we got to go back and change it. Great. You go back to the base model and you update, maybe it was this subdivision right here, and you go back and update it. You update it, great. Now, since all of these alternatives are children, ultimately children of the base, anything you do in the base is automatically going to be pushed down to all the children. And they're all updated, unless you specifically designated that value within that physical alternative. Now, how some other software packages work is they take a copy of the base, add the line, take a copy of that, add the line or 2, take a copy of that, and add all of your lines. Now you can see in the same circumstance where Mr. Modeler, Miss Modeler, 50 pipes were input incorrectly, you have to change all of the pipes diameters here, change all these, change all these, and change all these, and suddenly now you're up to, what is it, 200 pipes that you had to change instead of 50. So another way that you could actually end up doing this to yourself in WaterCAD and WaterGEMS is if you're not using the inheritance with scenarios and alternatives, but you're saving a file and changing the name, and then saving another file and changing the name, like actually going to File Save As and saving it as a different name. That's another situation where you can end up with having this situation at the bottom, to where you have multiple models that you're not able to leverage the inheritance anymore to make changes just to the base model. The differences between the different types of runs, as Dr. Walski was saying earlier during his presentation, for a steady state model, it's just a snapshot in time, and we'll only be using a few alternatives, a few building blocks to build a scenario, like an initial conditions alternative, the demand alternative, and the physical alternative. So pretty much those 3 just for a steady state run. To run extended period simulation, we're going to use operational alternatives. For a fire flow, we'll use the fireflow alternative and the physical and demand and initial. So it just kind of depends on the type of model run that we're going to do, whether or not we're going to use one more or less alternative or building block. Now that we're starting to get into, okay, well, you got to keep up with different scenarios and different alternatives, there's a tool to help you along the way and keep your sanity. Once you change a few things and you go off and do another project, you come back in a couple weeks and you sit down and you think, what the heck did I change and what was I doing between these two different scenarios? Well, we have a tool called Scenario Comparison. To do that, you'll go to Tools, Scenario Comparison, pick the two scenarios you want to compare to, and press OK. What it'll first do is flash up on the screen and show you, okay, Mr. Modeler, Miss Modeler, your demand alternative and your fireflow alternative are different. These two are different. Okay, great. Now it's giving you an idea what you did differently between the two scenarios. Now you want to see a little bit more detail and see what those changes were. So now you can go look at the differences between those two and see, okay, this one scenario had the C factors at 100, this other scenario had C factors at 130, and there was a few diameter changes as well. So now we're comparing one scenario to the other to see what changed. Maybe you're using this because you picked up a model from someone else and you're trying to understand their thought process, what they were doing, and what they changed. So this allows you to surface all of those differences. And sometimes, quite honestly, you could come up with two scenarios that there is no difference, they're the same. They're referring to the same alternatives, and there just may not be really much point to even have that scenario, two duplicate scenarios. You can see graphically those differences to see where they were and where those changes occurred, so you can better understand, okay, this is a subdivision. Now I understand why there's a difference here, or this is a connection. It doesn't exist today, so somebody was trying that out to see if that would work. Now I understand why that's there. And then at the end of all of that, you go through your scenarios, you run it, and then you start looking at the data. And that's the exciting part to me, is where we can tell the story. And that's what we're going to be getting into over the next couple of days, is you run the analysis, and then you start looking at the data, slicing it different ways, and trying to understand how to fix something or how to improve your pumps or whatever it is you're trying to do. And you're going to communicate the message through graphics and through color coding and charts.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.